What's up, good people? This is your boy, Mr. Bergman, here with section 5.4, the remainder and factor theorems. Today we're going to do the remainder, and then next video, we'll do the factor theorems. And you'll notice there's a slightly different color scheme going on. It's actually worth it if you're able to spend a minute, like less than a minute, finding red and blue writing implements, then it'd actually be worth it. I would say it's not required, it's not 100% necessary, but if you can, pause the video, take a minute, and find something red to write with and blue to write with in addition to your pen or pencil. So pause the video, get those writing implements. All right, so maybe you have them, maybe you don't, but I do want to say that I'm going to be connecting conceptually. Every time there's a divisor or an input, I'm going to write them in blue, and I'm going to connect them with an idea. And then anytime there's an output or a remainder, I'm going to write them in red, and I'm going to connect those conceptually too. And I hope you can, if possible, you can do the same. If not, don't worry about it. Anyway, if you notice here, let's do a polynomial. You see 2, -1, 0, 1, 2, -1, 0, 1. Even written below, it's 2, -1, 0, all the way down. It's going to be the same polynomial that we're starting out with, 2x cubed minus x squared minus 1x squared plus 0x. It's just absent there, so this is a placeholder, and then plus 1. We're going to start with the same polynomial, but what we're going to do is we're going to switch up what we divided by. So we have different divisors each time, and we're going to see what effect it has on the remainders. Okay, so the blue divisor starts with 3, and there's 3 right here. The blue divisor is 3. You're going to take the 2 and move it down here. That's 2 times 3 is 6, plus -1 is 5, times 3 is 15, plus 0 is 15, times 3 is 45, plus 1 is the remainder. The red remainder is 46. Okay, let's duly noted. Let's do the next one. If the divisor is 1, that means it's x minus 1 here. Oh, and translate to a polynomial. So the result, 2, 5, 15, is 2, 5. This should be 15 here. (15) 2x squared plus 5x plus 15 with a red remainder of 46. And all right, so now we got another blue divisor here of 1, x minus 1. So same starting polynomial, but we bring down the 2, multiply by 1, we get 2, plus -1 is 1, times 1 is 1, plus 0 is 0, times 1 is 1, plus 1 is 2. So the red remainder is 2 when the blue divisor is 1. Let's just switch it up. Let's say it's x minus 0. The blue divisor is 0, blue divisor is 0. So all these, anytime you multiply, it's 0. And so you bring down all these, anytime you add, it's just the same thing here. So the red remainder is 1. This is just, if you're going to translate this result to a polynomial, it's 2x squared minus x plus no constant is a remainder of 1. Let's switch it up and make it -1. Okay, so if the blue divisor is -1, blue divisor is -1, this becomes x plus 1. And let's see, bring down 2, multiply by -1 is -2, plus -1 is -3, times -1 is 3, plus 0 is 3, times -1 is -3, plus 1 is red remainder -2. Red remainder -2 translates to a polynomial 2x squared minus 3x plus 3, 2x squared minus 3x plus 3. There it is. All right. Completely and totally unrelated idea. Let's have a left field. Let's also do an input-output table. And we're going to take all these blue divisor numbers over here on the left, and we're going to put them into the actual function. You remember 2x cubed minus x squared plus 1. That's the same polynomial we had here. And if you plug in 3, 1, 0, -1 as blue inputs, then the outputs are the red outputs are going to be 46, 2, 1, -2. Wait a minute, those were the remainders. Remainder. The red remainders and the red outputs were the same. Anytime this is not just happens to be all these numbers here, but any number you put in as a blue input will give you the red output. The blue divisor would be the red remainder. Turns out it's not just true with this polynomial, it's true with any polynomial. Here's the big idea. If you do this often enough, you'll notice a pattern. At the red output of f of a, remember blue of a, the blue input, And the remainder, when you calculate f of x divided by x minus a, are going to be equal. That's the remainder theorem. The remainders theorem says basically that the output and the remainders are going to be the same. They're going to be equal to each other. Red output and red remainder are going to be equal. So check this out. Let's verify this one more time. So a different polynomial, I'm not going to worry about translating it into a polynomial. Let's just do this synthetic division. So 2 times, bring down the 1, times negative 2 is negative 2, plus 7 is 5, times negative 2 is negative 10, plus 5 is negative 5, times negative 2 is positive 10, plus negative 4 is 6. More synthetic division. Let's change up the blue input to be negative 1. Bring down the 1, times negative 1 is negative 1, plus 7 is 6, times negative 1 is negative 6, plus 5 is negative 1. Switch the sign, you get positive 1, times, obviously, plus negative 4 is negative 3. 1, bring down the 1, multiply by 1. All these, when you're multiplying by 1, all these numbers, 1, 8, 13, are going to be the same, 1, 8, 13. When you add them, this is what you get 9 as the red remainder. Bring down the 1, multiply by 2, you get 2. 7 plus 2 is 9. 2 times 2 is 18, plus 5 is 23. Times 2 is 46, plus negative 4 is 42. So these were the blue inputs, and these are the red outputs. And lo and behold, if you actually put them in here, you get negative 2, negative 1, 1, 2. You actually get the exact same numbers as outputs. You can calculate them. The red outputs are here, and they're all equal to the red remainders. Isn't that really fun? The remainder theorem holds up. The output of f of a and the remainder, when you calculate f of x divided by x minus a, are going to be equal. The red stuff is equal. That's what the remainder theorem says. So, in synthetic substitution, we're using synthetic division's remainder to calculate the output of a function. So, if the remainder and the output are going to be the same, sometimes if you want the output, sometimes it's just easier to calculate the remainder. So if you want so the instructions might say use synthetic substitution to calculate the output. So we have the input here, and we want the output, and we have the input here, we want the output. So instead of actually calculating the output, let's just calculate the remainder, because they might as well if they're equal. So let's say we wanted to figure out if the input was negative 5, what's the output? And you can see, bring down the 1, times negative 5, plus negative 8 is negative 13, times negative 5 is 65, plus 6 is 71. So if here the blue divisor and the red remainder are here, they're going to be equal to the blue input and the red output. If the input is negative 5, then the output is going to be 71. I don't even have to, if I feel like synthetic substitution is easier, if synthetic division is easier, then I might as well just do that instead of substitution. Like I could, if I wanted to, put negative 5 in here, square it, and then minus 8 times negative 5, and then add 6. The answer is going to be 71. But maybe synthetic division is easier than substitution. Let's do it again. Because the instructions say make an input of 2. Well, if the input's 2, I might as well just make the divisor 2. The blue input and the blue divisor could be 2. And so then bring down the 1, and then multiply by 2, you get 2. Times negative 8, you get negative 6. And then times 2, you get negative 12. 6 plus negative 12 is negative 6. The red remainder is negative 6. So that means the red output is going to be negative 6 also. You could put 2 in here. Let's see, 2 squared is 4, minus 8 times 2 is 16, plus 6. Yeah, you do get negative 6 here if you were to substitute. But maybe synthetic substitution is easier. It doesn't matter. You can do either one. They're going to be the same. Whoa. All right, so here we have a very huge polynomial. And I'm not going to actually run through the calculations verbally here, but you might be able to see, like, plugging negative 5 as an input to a giant polynomial like this, synthetic division might be easier. So let's do that instead. F of negative 5 would look like this. You put negative 5 in, and as the output you get negative 4,450. maybe synthetic division's easier than substitution. In this case, it might be. Okay, so yeah, you don't plug in 2, and you get here the output of negative 26. So f of 2 is negative 26. There's no input or output table needed because instead of an input-output table, you're using synthetic division. That's what that's the power of the remainder theorem. All right, here's how it might look on the SATs. Consider the polynomial p of x is equal to kx cubed minus 5x squared plus x plus 3. Not uncommon for those SATs to test you on something by asking you to do exactly what Mr. Bergman or any other math teacher has taught you how to do, except that there's a letter where you expect a number to be. And the first step is just going to be to do what you normally do anyway, with dancing around the fact that you've got a letter where you expect a number, and then somehow calculate what that number should be based on a condition that they give you. So you get this polynomial and find the value of k such that, here's your condition, find the value of k such that the remainder is 10 when p of x is divided by x minus 1. So what they're testing you here is the remainder theorem. And so what you've got to do is connect the red remainder to the red output and the blue divisor to the blue input. Remainder is 10. Okay, so really what you extract from this information is the fact if the remainder is 10, then that means the output's going to be 10. And if the divisor is 1, or if the divisor is x minus 1, then the input is going to be positive 1. So really what you can do is, instead of trying to think about this as division, you could think about this as input-output. So this is the information they give you. These are the knowns, and this is what you can translate them to because you know the remainder theorem. So if that means that I could put the 1 in as the input and an output would be 10. So if the 1 is the input, 1 is the input, then the output's going to be 10. And lo and behold, we arrive at an equation that's not too difficult to solve. We can just simplify all these numbers, especially because the input is 1. It becomes k minus 1 is equal to 10, and then k is equal to 11. So going from here to here requires knowledge of the remainder theorem. But if you can do that, then actually solving this, the mechanics of solving this is not too hard. Here's another way of doing the same problem that has nothing to do with the remainder theorem. If you are not able to translate this to the input and output, then what you could do is you could just say, all right, well, if it's division, then I'm going to divide. I don't know what this polynomial, what k is, but I might as well just put it into synthetic division. So the remainder is 10 when it's divided by x minus 1. So I'm going to put a 1 here, bring down the k. When you add, multiply by 1, you get k. Add negative 5, you get k minus 5. Multiply by 1, you get k minus 5. Add 1, you get k minus 4. Multiply by 1, you get k minus 4. Add 3, and you should get k minus 1, but you could also get 10 because that's the remainder. So there are two ways of figuring out what should go here. The first one is that they just flat out say that the remainder is 10. The second one is when you calculate this, you get k minus 1. So therefore k minus 1 must equal 10, or k is equal to 11. Either way, the answer is 11. All right, we need another skill. The reason we need this skill is because we need to figure out, I want to convince you why the output actually does equal the remainder. It's also going to be a skill. This new skill is also going to be tested on alex.com directly, so might as well learn the new skill. And the new skill is just rewriting division as multiplication. So if you see something like 31 divided by 5 is equal to 6 remainder 1, you could change that around. You notice that the order is actually not the same. 31, 31, 5, 5, 6, 6, 1, 1. The order is the same. The only thing that changes is that instead of a division, you write an equal sign. Instead of the equal sign, you write a multiplication and add addition right here. But the order is still the same. So if you see division here, you could rewrite that as multiplication. This 31 is really equal to 5 times 6 plus 1. Okay. This 56 divided by 10 is equal to 5 remainder 6. Well, it's really just the same thing as 56 is equal to 10 times 5 plus 6. And 58 divided by 7 is 8 remainder 2. Well, that's the same thing as 58 could be equal to 7 times 8 plus 2. I'm rewriting these divisions as multiplication. And so generally speaking, you can say that the dividend divided by the divisor is equal to the quotient plus remainder. What's really just the same thing as the dividend is equal to the divisor times the quotient plus the remainder, the red remainder, and the blue divisor. All right, so let's do that with polynomials now. So you can see here we've got division, equal sign, equals, times, plus. No different. We're just when it comes with the symbols. Symbolically, it's all going to be the same. However, we're going to change. We're going to be using with x's now. So it used to be this divided by this is equal to this with red remainder of this. Now it's going to be this is equal to blue divisor times x plus 2 plus red remainder here. Let's do that again. You can see here this divided by this is equal to this remainder of this. Well, then you've got this is equal to this times this plus this. Here we've got this divided by this is equal to this and remainder this. And now we can change it so that this is equal to this times this plus this. Okay, so now that we're good at changing things around, let's do that here. As a follow-up, let's substitute the divisor as the inputs. If we know they're the same, or let's make them the same here. Let's make the divisor equal the input. So if the divisor here is 1, like we know it is, the divisor is 1, then let's also make that the input and see what happens. If the divisor is equal to the input, so 1, if let's actually substitute 1 in here, we get 1 minus 1 is 0. And so then, therefore, we have the red remainder over here, and the red output over here of the function. And lo and behold, this middle term cancels out; it turns into 0. So therefore, the output is equal to the remainder. Interesting. If the divisor is 2, let's also make it the input. So what happens when we make the input equal to the divisor? Let's substitute in 2. We get 2 squared plus 2 plus 4. And as an output, we get 6. This is the entire function here. When we've rewritten it, we have rewritten multiplication over here. It seems like this 2 minus 2 turns into a 0. And we multiply it by some other number. It doesn't matter what it is, you're going to get 0. So this whole term cancels out, and you're only left with the remainder. One more time. If you had this polynomial right here, x cubed plus 2x minus 6, and you made you set the divisor as the input, you made them equal, then input was 4 into this polynomial, and the output is 66. This over here on this right-hand side, the divisor actually is 4 minus 4, this is 0, and 0 times anything is still 0. So this whole term cancels out, and you're only left with the remainder, 66. So that's kind of why the remainder theorem works. It's because written in this form, most of it all cancels out, and you're only left with the remainder, 66. The output equals the remainder. All right, so here's what it might look like on alex.com. Alex, the instructions might say dividing p of x. They don't even tell you what p of x is, but dividing by some polynomial function p of x by x minus 1, here's the blue divisor, yields a quotient q of x and a remainder, red remainder of red 1. If q of negative 1 is equal to negative 3, find p of negative 1 and p of positive 1. All right. So first step is going to be remembering how to first step is going to be taking what they've, reading this p of x divided by x minus 1 will symbolically look like this. So I encourage you to write this down. P of x is divided by x minus 1 is equal to, I don't know what the q of x is, they don't tell me, but they do tell me what the remainder is. So we're going to use we're just going to read the knowns here and translate them into an equation symbolically. P of x divided by x minus 1 is equal to q of x times r with a remainder of 1. Now we can translate that, we're doing our newfound skill of taking division and turning it into multiplication, translate that into p of x is equal to x minus 1 times q of x plus 1. This second version is actually going to be way easier to deal with, because what we've got to do next is find what p of negative 1 is. Let's use this second version over here, the version with multiplication. P of negative 1, therefore, would be And then instead of x minus 1, I'm going to rewrite this as negative 1 minus negative 1 times q of negative 1. That's the input, plus 1. Now, I don't know what q is, but they did happen to randomly tell me what q of negative 1 is over here. So I got a little, they gave me that like random piece of information that's actually going to help me calculate everything on this side. Q of negative 1 is, as they tell me, is randomly equal to negative 3. I don't even know what q of x is. I don't know what q of, I don't know what the input would be. I don't know what the output would be if the input were 5 or 10 or negative 3. But if the input's negative 1, then I can say the output is negative 3 for this q of x other polynomial. Then minus 1, negative 1 minus 1 is negative 2, and the remainder is 1. So 2 times negative 3 is positive 6, plus 1 is positive 7. So I don't know what the polynomial is, but I do know that if I happen to put negative 1 in, I can simplify everything out and I get positive 7. Here, if I put positive 1 in, then the x minus 1 turns into 1 minus 1, and I don't know what q of 1 is. That's just, this information hasn't been given to me in the instructions. The remainder is 1. But lo and behold, it doesn't matter that I don't know what q of 1, the output of q of 1 is, because when I take 1 minus 1, it's 0. 0 times anything is going to be 0. And I'm going to add 1 to it. So you tell me, what is 0 times anything plus 1 here? And that's it. Thanks for paying attention. And bring your questions to class. I'm sure you've got plenty, because this is, when it comes to conceptual stuff, this is pretty heavy. Oh, and by the way, my favorite color to wear is, as you might guess, blue, because that's what I'm wearing right now. Take care.